Ferrocells are interesting devices that show the effects of magnetic fields. Unlike the classic demonstration of iron filings on paper with a magnet underneath, ferrocells show how the fields change as the magnets moved without the filings clumping up. Because they're so easy to build, they make perfect school science projects for any child old enough to use an X-Acto knife safely. Here's how to make one in just 1 hour. Start by cutting a 20 by 22-inch rectangle out of a sheet of black foam board. Cut 5 by 5-inch squares out of each corner, and then an 8-inch diameter circle out of the center of the central 10 by 12-inch rectangle. Crease the dotted lines, and then fold the panels up. Secure them with tape to create a box that looks like this. From another piece of foam board, cut a 9 7/8 by 11 7/8 rectangle and cut another 8-inch circle in its center. This rectangle is slightly smaller than the box, so it can fit inside of it. Use a sticky-backed LED string to line the inside of the smaller rectangle circle. These strings come with one end connected to a power plug that hooks into the supplied transformer and the other equipped with loose wires. Use the plug end if the ferrocell is for home use. Use the wired end if it's going to be used for a science fair, so it can be battery powered. This avoids talking a maintenance worker into running an extension cord to your display. And here's what it'll look like. To make things a little more interesting, I've lined half of the LEDs with red cellophane and the other half with blue. This brightens things up a little bit. This one I used the loose wires because I'm planning to run this off batteries. You only need one row of lights, so you'll need to cut the string off once it's gone once around the circle. Be careful to cut only where the tape is marked with small pictures of scissors. Cutting anywhere else will prevent the string from lighting correctly. It's not critical if the string ends up being 1 or 2 LEDs too long or too short. The adhesive backing on the back of the LED string is pretty sticky, but to be safe, if you're not going to cover it with colored cellophane, I'd use some clear tape several places around the circle to make sure it doesn't come off. This is especially important where the wires connect, because these tend to be pushed around and can peel off the LED string very easily. Push the light board into the bottom of the box so that the lights are 1.5 inches below the top surface. If it's too tight, trim a little off the edges. If it's too loose, secure it with hot glue. Poke a hole in the side closest to the wires and feed them through it. Now take a piece of black construction paper and cut a 5 1/2 inch diameter hole in its center. This acts as a baffle to block the bright light around the edge of the ferrocell that washes out the edge of the image. Next, mix 1 part ferrofluid with 1 part WD-40 and stir well. I've tested many different ratios and combinations of different liquids, and this mix provides the best images. Only a very little ferrofluid is needed, so buy the smallest amount possible. If this is for a school science project, the science department may stock some that you can have for free. Place a clean 10 by 12-inch sheet of glass on a wood base thick enough to get your fingers under the glass. This will help control the lowering of the upper sheet of glass. It will do in just a minute. Holding an eyedropper close to the glass, carefully squeeze out 20 drops in the center. Try to avoid getting any air bubbles. Next, place the second piece of glass about 1/2 inch from one end and hold it with your thumb. Now very, very slowly lower the top glass down until it just barely makes contact with the ferrofluid. Once it does, slow down moving, because if you drop it too quickly, you can create voids that will make it hard to use. Now just walk away and let it sit for about 10 minutes. What will happen is over time, the ferrofluid will slowly spread. all by itself. If you try to press down in the center to speed things up, you can get more unevenness and make things even worse. Actually, you could do this step first, and while the ferrofluid is spreading, work on the rest of the body. And that's it, you're done. Well, almost. If the Ferrocell is going to be used in a bright room, you need something to prevent glare from washing out the image. To do so, take a third sheet of foam board and cut out a four-sided box the same way the main body was made, only this time the hole in the center of the central 9 by 12 inch rectangle is only 3 inches in diameter. This hole is where people will look down through to see the Ferro image. The sides are 9 inches tall, and the bottom is left open so that people can reach in to move the magnets around. This can be made out of a third sheet of foam board, like I said, or out of the scraps from the first two sheets. And here it is all put together. I've used clip leads as a simple way to connect two 6-volt batteries in series to the lights inside the box. This is the glass sheets with the ferrofluid in between them, the baffle so that the edge lights don't wash out the image. I'm going to turn the lights off to show it, but if I was going to leave them on, I put the glare protector like that and look down through the hole, and I'd be able to see just fine. And here's what we get. Looking pretty good. The stronger the magnet, the better the image will appear. I recommend N52 rare earth magnets, which have the highest rating. Different magnets or combination of magnets produce a wide variety of patterns, so by all means, experiment. And that's it. A working Ferrocell in under an hour. The only thing left to do is figure out how Ferrocells work, which is what follows, but isn't really necessary if all that's needed is a visual representation of magnetic fields in action. It's tempting to assume that the lines we see are following the magnetic lines of force, but if we overlay the Ferrocell with the actual magnetic field lines, we can see that while the poles are close, as we move around to the sides, not only don't the Ferrocell lines line up with the field lines, they're actually perpendicular to them. Clearly, something more complicated is going on. But when I searched the internet and YouTube for an explanation, I couldn't find any that made sense. A few websites tried explaining it, but the more I studied what they were saying, the less sense they made. Now, I have master's degrees in mechanical engineering and plasma physics, so while I may not be the sharpest stick in the bundle, I can usually stumble my way into a qualitative understanding for most complicated explanations. But these ended up reading more like technical jargon designed to sound impressive more than actually explain something. So, I came up with my own theory. I offer it without any proof other than it seems to make sense. But before beginning, the large number of intersecting lines created by the 39 lights that power the Ferrocell make it difficult to see what's happening. So let's switch to a unit with only one light. Just for fun, I used a blue LED. We can now see that each light in the Ferrocell produces 3 lights, one out of the pole and 2 more projecting perpendicular to the sides of the magnet. As we move to the left, the pole ray bends to the left. The left perpendicular ray bulges up, and the right one moves down. The opposite happens when we move to the right. Any theory that claims to explain how a Ferrocell works has to be able to account for both the 3 rays and how they move. This image shows the 3 rays and how they relate to the magnet's field. Unfortunately, what I believe is going on is too complicated for this two-dimensional representation. So, get ready to go 3D. And here we are. What this image tries to show is that magnetic fields don't surround magnets in lines, but in a continuous field, depicted here as a series of cones that emanate from the North Pole, expand like the bell of a trumpet, and then fold backward as they converge towards the South Pole. The field surrounds the magnet in 3-dimensional curved surfaces shaped a little like an egg. The next piece of the puzzle to how Ferrocells work is understanding the scale of the size of the particles in the ferrofluid to how thick the layer of ferrofluid is between the 2 sheets of glass. This layer averages 15 micrometers, which sounds pretty thin, but the particles of magnetite in the ferrofluid average only 6 nanometers. That's 2,000 times smaller. To put this in scale, if each particle was the size of a car and you line them up bumper to bumper, they'd make a line 8 miles long. What this means is that as thin as the layer appears, in reality, it's thick enough to support extensive structure once the magnetic field turns on. And it's this structure, I believe, that creates the lines we see in the ferrocell. Let's look at a layer of ferrofluid near the bottom pole. Imagine looking at it from the side. Here's what I think happens. When the magnet is placed on the ferrocell, its field causes the ferrofluid particles to line up end to end in chains that are parallel to each other, forming curved surfaces. Now, in reality, there are no surfaces, but a continuum of change throughout the volume following curved paths. But the idea of surfaces makes it easier to explain what's going on. I'm afraid we've reached the point where the physics gets a little heavy. The particles of magnetite are so small that they're only 1/100th the size of the average wavelength of visible light. This means light doesn't reflect off of them like it does off a mirror, but is scattered randomly in all directions. It's called Rayleigh scattering. But in a magnetic field, since they're lined up close and end to end, they don't behave like individual particles, but instead like a long, thin wire, which can reflect, or at least preferentially scatter, light in specific directions. Accepting that, then when light from one of the LEDs shines on one of these virtual surfaces, because the surface is curved, only light from one small area reflects at the proper angle to make it into our eyes. This happens at each surface, but because they're slightly spaced apart and at slightly different angles, we see the result as a continuous line. The test of this concept is if it behaves the same as what we observed earlier. Going back to the one light ferrocell, light from the LED illuminates this entire area, which bows outward because it's curved in 3 dimensions. The only light we can see is what's reflected off the center line. But if we move off to the left, now the only light we can see is what comes out of the LED at a slight angle and strikes this zone of overlapping surfaces. And since these are curved to the left, the beam of light also appears to curve to the left, which is exactly what was observed. Now let's try to explain the 2 rays that come off perpendicular to the sides. Here we run into a problem with this drawing, which shows the field curving gently out of the sides and the end of the magnet. In reality, these curves are much sharper, coming out near the center of the pole and very quickly curving around towards the upper pole. In this area, the same process explained for the pole takes place. Only small areas of each surface reflect light at the correct angle for us to see. If you can imagine tighter curves, then you'll be able to imagine that, just as before, each one contributes to the observed light. If we move to the left, the line not only curves to the left as before, but because the light is below the ferrocell, reflecting or scattering off the underside of the surfaces, and our eye is above it, the line of areas that can reflect light into our eye climbs up the face of the surfaces, causing the line to bulge upward. Again, what we observed. This is just my theory, and I may be completely wrong, but it seems to make sense and is consistent with observations. I'll continue to research how ferrocells work, and if I find a better explanation, I'll post a follow-up video about it. Ferrocells are interesting and great science projects, so if you're planning to build one, I hope you found this video helpful. My next video is going to be about building a pendulum-type drawing machine that creates traces in a bed of sand. Until then, I hope you'll visit my main website at waynesthisandthat.com, where you can find out how to build a cloud chamber that captures subatomic collisions, or discover the very strange world of lucid dreaming. Thanks again for watching.